Okay, welcome back to the third day on the SIMPA mini course on stochastic optimization for large-scale machine learning problems. In the previous classes, we talked about stochastic gradient descent and talked about mathematical theory behind it, how we can show that it converges even with very complicated non-convex functions. And there were some questions about how do we choose the step size and how shall we determine it from the beginning, this diminishing step size sequence, or can we choose it on the through while the algorithm runs. And so I wanted to show you a recent paper on a method which chooses the step size while the algorithm runs, and depending on each step it looks for the best step size possible. And remember that if you have a big step size, especially if you are working with a fixed step size algorithm, then you converge faster, but you do not converge. You just converge to a neighborhood of a minimizer, but that neighborhood gets bigger when you choose a bigger step size. So there is this balance. If you can, by choosing big step sizes, you can converge faster, but then you don't converge maybe very close to the minimizer. So there is this trade-off here. So I'm going to talk about a method which changes the step size during the run of the process of the algorithm. So as before, we are going to say we have these training points, and we want to minimize this empirical risk function, where the whole average is called the loss function evaluated over this data, and if each fi is the loss function evaluated at a specific point xi, yi. And the stochastic gradient descent, today at the beginning I'm just going to assume that it runs like this. You start with an initial point, you choose a maximum iteration number t. The camera is gone, okay. Please follow me. Yes. All right. You choose a maximum iteration number t, and then you choose an index or a data point uniformly randomly from the set of training points, and then you calculate the gradient of the loss function just at that point, and move in the opposite direction with a step size alpha k, which is determined from the beginning. All right. Of course, instead of choosing only one data point, you can choose a mini batch of them, but we are going to just simplify things for today's sake. All right. So I'm going to talk about stochastic line search. What it uses is actually a recent paper from 2019 that you can see here. And what it does is it applies this classical approach of Armijo line search from classical optimization to stochastic optimization. Armijo line search is basically you start with a maximum step size, let's say alpha max, and then at each step, to take this stochastic gradient step, you look for the biggest step size alpha k, always smaller than alpha max, such that it satisfies this inequality. And what is this inequality? This is the function's value, but it's the loss function evaluated at ith data point, that loss function evaluated at this point, at this parameter. This is exactly when you take the gradient step. So you take the gradient step, you calculate the, let's say, the stochastic function value at that point. You calculate the stochastic function value at the starting point, which there's a typo here, you have to write omega k here. And then you look at the difference. What you want is you want the difference to be small, to be negative and small. And then you basically, our condition is you want it to be smaller than or equal to some c, which is a hyperparameter to be chosen from the beginning. C times alpha k times the squared norm of the stochastic gradient. And then you find the biggest alpha k satisfying this inequality. You choose this c from the beginning, and you use cross-validation, any validation method to choose the best c that works for your problem. So, of course, one question is, okay, but how do you choose this alpha k? How do you solve this equation? How do you find the biggest alpha k which satisfies this equation? And we are going to use backtracking. So the algorithm now, the algorithm on stochastic line search turns to this. You start at a point, you provide the algorithm with alpha max and c. Then each point you choose a data point randomly, uniformly. Find alpha k, which satisfies the Armijo condition, the biggest alpha k. And then you take a step with respect to that alpha k. So at each step, you choose the best step size that you can get. Best means the biggest step size you can get that results in a decent, sufficient descent in the function, stochastic function value, not the full function value. Because it's very expensive, computer time cost-wise, to calculate the function's value for the whole data. So what you do in the stochastic cases, you just use stochastic function values and stochastic gradients, so that runtime-wise, the cost doesn't grow much. And okay, but how do you find this point? And there's this alpha k which satisfies this equation. There's this classical method called backtracking. What you do is you start with maximum step size allowed, and then you see if the Armijo condition is satisfied or not. If it doesn't, then you multiply your alpha k with some constant gamma, which is smaller than 1. So you decrease the step size and see if the Armijo condition is satisfied or not. Still, if it's not satisfied, you multiply it with gamma again, so you make it shorter, and you keep on trying this until you find a point which you find an alpha k which satisfy the Armijo condition. And since you are decreasing the step size gradually, the point that you find is an approximation of the biggest alpha k that satisfies the Armijo condition. So we are going to use Armijo line search using with backtracking. So this is what the algorithm looks like now. So I'm going to introduce 2 more modifications. So each step, randomly, uniformly choose a data point, and then using backtracking, find the biggest alpha k which satisfies the Armijo condition. Take your step, and then what you do now is, once you take your step and move to another iteration, you restart this process. You restart your step size from alpha max, and then do this again and again. But assuming that since your function is continuous and you are not moving far away from the previous point usually, what you expect is the geometry of the function doesn't change a lot from one point to the other. So once you choose a smaller step size that works for the previous step, what you expect in the next step is you need a step size that is similar to the step size that you use in the previous step. So instead of starting from alpha max each time, what would make the algorithm run faster is, instead of starting from alpha max, you update your alpha max with you set it equal to alpha k that you found in the previous step, and you start from there. And then you don't have to diminish the alpha k again and again with many iterations. One thing is, if you do it this way, especially in deep learning problems, that you use a lot of iterations. You go over the data again and again. And this way, your step sizes diminish quickly, and after some while, your algorithm will stall. It will stall at some point, and it cannot move much because your step sizes were small. To prevent that, what you want is, once in a while, you want to reset your maximum step size, alpha max, so that you give the algorithm a chance to start from a big step size, and hopefully the algorithm runs faster, with a faster rate. So what you do is you choose a capital N, and whenever in every n step you reset your alpha max, and you can choose different ways how to reset your alpha max. You can return to the original value, or you can modify it with some algorithm that you choose. And all right, so what is usually done is you reset your alpha max in every epoch. An epoch meaning what you do is in practice, instead of choosing a random point every time, what people do is they shuffle the data, and they start from one point and go all the way to the end, one by one, going over these training points. So once you go over the all data, then you start again from the beginning, and each time you do this, it's called an epoch. And finishing one epoch is a good time to reset your maximum step size. And if you want to prove that this algorithm works and it converges to a point, a minima, at least a stationary point, what you need is the continuous differentiability of the objective function, and you assume that it's Lipschitz constant. It's Lipschitz continuous with the Lipschitz constant L. And then in this paper, the authors also assume a second assumption which is called strong growth condition, which says, okay, f is lower bounded by f star as before, but instead of, if you look at these, expected values of the square norms of these stochastic gradients, before what we had was, so before we assume that this expected value is a constant time plus rho or mg back then times the square norm of the full gradient. Now we are just assuming that this is smaller than or equal to some rho times this square norm. So this is a stronger condition. We are assuming either there is no noise in the gradients, or the noise is proportional to the full gradients norm. And this is satisfied for problems where the minimum of the problem is exactly happening when the gradient is 0. And this condition tells you that at that point all the stochastic gradients are also 0. So in those kind of problems where it's called interpolating problems, the loss function is minimized at the value 0. So for those kind of problems where your model interpolates your data, then this condition is satisfied. And then you can give a convergence proof for non-convex functions with a similar rate that we had before, different constants, of course. I'm going to skip that proof. You can find it in the paper. And if you see the proof, it's actually pretty similar to what we have done yesterday. Just a little bit difference because we are changing the step size, but they are bounded by the maximum step size. And actually what you can do is you can also bound these steps that you get out of the Armijo line search from below. And then you can come up with a rate like this. And okay, I'm not going to cover this today. I'm just going to leave it to you. But what I want to do is I want to see how it performs against SGD. And I'm also going to look at it against a very popular optimizer called Adam, which we are not going to see actually in this class. But since it's nearly the default optimizer, I'm going to put that into these experiments to compare performances. And okay, so it's backward. So this is my first experiment where I'm looking at the MNIST data, and here I'm using a neural network as the model where it has only one hidden layer with 1000 nodes, and which are densely connected. Each node is densely connected to the other. Each node is connected to the other, and now in every step. All right, so here are some experiments with respect. Okay, we have Adam with its default learning rate 001, and then SGD with its default learning rate with 0.1. And actually these are really the best performing constant learning rates here. And then we have SLS with learning rate 1. C is chosen 0.1 here, and gamma is 0.9. And as you can see, in terms of training loss, it goes lower than every other method that we see here. And in terms of accuracy, it behaves similar to SGD, maybe a little better because maybe it's converging to a good accuracy before SGD. But this is in terms of epochs, but this algorithm calculates the function value and sometimes the gradient at that point again and again, right? So it makes more calculations in every iteration if the Armijo condition is not satisfied. So let's also look at how it behaves in terms of runtime. So these runtimes are calculated at the same computer. And as we can see, even with, as we can see, even with the runtime, it works pretty well. SGD seems to go below that at some point, but if you look at in terms of accuracy, yeah, SGD is sometimes better, and then they converge to the same accuracy in a short time, in a sense. So, all right, this is what happens in runtime. Let's look at another problem. This is the CIFAR 10 data set that we have seen in the very beginning of this class. It is classification of these pictures, which are 32 by 32, and each are labeled. There are 10 labels that these pictures are from. There are pictures of trucks, animals, 10 many objects, different objects, 10 many labels. And then what we use here is an convolutional neural network, a deep neural network actually. I think nearly 34 levels inside, hidden levels inside. It's a convolutional neural network. It's a little bit more complicated than a densely connected network, if you know what it is. And if you look at the performance here now, SLS performs much better than ADAM or SGD. But keep in mind that SGD and ADAM is running with a constant step size. There is no scheduling or a schedule for how to diminish the step size. But SLS is doing it by itself, so it's a kind of auto-scheduling method. And it performs very good, much better in terms of epochs and in terms of runtime in the training function. But what about accuracy? If you look at accuracy, it's also performing better. It's converging to a point where the accuracy is better than other two models. So here is another example. This time the same model, same neural network model, but now it's used on this new another data set called CIFAR 100, similar to CIFAR 10, 32 by 32 color images of objects, but now we have 100 objects, so 100 labels. And if you look at the performances with the same hyperparameters and these learning rates, same learning rates, now SGD seems to be working better at the end actually, although ADAM is always a little bit faster at the beginning to converge for the first 40-50 epochs, but eventually SGD and SLS goes below that. And SGD seems to be better than SLS. I took this example to show you that actually even though SGD goes to lower values in terms of training loss, if you look at the accuracy, even in both in epochs and runtime, if you look at accuracy, SLS is performing much better than SGD. So this is something that you always can see in these deep learning problems or large scale or any machine learning problem, that even though your function performs good on the training loss, actually in terms of accuracy it may converge to a worse point. And we have already seen that, right? If you look at gradient descent method, which uses the full batch, and the stochastic gradient descent, which uses mini batch or just one data point every time, so it uses stochastic gradients. Even though the gradient descent method can converge to a lower minimum, the generalization power, the accuracy on the test data is better for SGD most of the time. And we gave some intuition by experimentally, we looked at this results from a paper that which claims that SGD actually is converging to flat minima, and that has a better generalization power or probability than where SGD convergence, which is a sharp minima. So again, you see this phenomena a lot, and this is what makes stochastic optimization for machine learning harder than, in some sense, classical optimization problems, because although you're using the training function to find the minimum, actually what you really want to do is maximize your test accuracy or minimize your testing function. So this adds another level to our problem. All right, so now I'm going to switch to another method for stochastic line search. This time, instead of backtracking, we are going to use model building. I'm going to explain this. This is from this recent work by Birbil, myself, Onay, and Öztoprak, from this paper that will appear soon, at least on arXiv, and I'm going to send you links once it's online. All right, so similar problem, we want to minimize the empirical risk. And okay, this is what we are going to do. Similar to SLS, we are going to take a trial step using the SGD step. So we are going to calculate a stochastic gradient. Here I'm going to call it as GK. It's either the stochastic gradient evaluated for one point or for a mini batch. And at each step k, you multiply it by negative alpha k. Alpha k is the step size. That's your SGD step. Then you take the step, but you don't stop there and move to the next iteration. You see if that new point satisfies the stochastic Armijo condition. If yes, then it's fine. Okay, now stochastic Armijo condition, I denote it this way. Fkt is the stochastic function value at the trial step, and Fk is the stochastic function value at this point where we started the iteration, and C is this hyperparameter as before. And if Armijo condition is satisfied, okay, you stop at that step. So you just take a stochastic gradient step. And if the condition is not satisfied, this time we are not going to do backtracking or Armijo line search. What we are going to do is we are going to build a model at these points, around these points, which approximates the function. It's a quadratic model which approximates the function. And then we calculate its minimum, the step which reaches its minimum, and then we are going to use that step to move to the next point. And if this model approximates the function well, hopefully the step that we are going to take diminishes the value of the function, decreases the value of the function fast enough, hopefully, that the algorithm converges. But the difference is we are going to do it just once. We are going to build the model and move to its minimum if the Armijo condition is not satisfied. So let's look at this picture which explains what we are doing here. So we are at point xk, and then we take a gradient step and move to this trial step, but we don't take it yet. We check the Armijo condition, right? If the Armijo condition is satisfied, then okay, we stop at this point and move to the next iteration. So we just take a stochastic gradient descent step. If the condition is not satisfied, we are going to build a model at these 2 points and move to its minimum, all right? And we will build the model so that this minimum, this length sk that we are choosing is smaller than skt, and it doesn't close to the starting point or the end point where we know the function is not decreasing, right? If it's not decreasing here because it's the starting point, and the function is not decreasing here because we already checked the Armijo condition. So we don't want this step to be close to here or here. So we will build our model such that this is satisfied. But one thing that you see which is different from SLS is we do it only once. But more importantly, actually, we are not just decreasing the step size. We are also choosing another direction to move. So we change the direction and we decrease the step size at the same time. So, and we do it only once. We don't check the Armijo condition again. All right. One thing that we should also mention here is there's another side to this model building approach in this algorithm is when you have a neural network, and in popular implementations of those with these popular libraries like PyTorch or TensorFlow, what you see is they group these layers inside the neural network, and you apply your algorithm to each of these parameter groups separately. Each layer gives you a group of parameters, and you apply your algorithm to these separately. What we are going to do here is since we are building a model and changing the direction with respect to that model, we take advantage of that and the parameter groups. So we do it for each parameter group separately. All right. So for each parameter group, we build a model. So we take this trial step with respect to the parameter group at hand, choose a trial point, check the Armijo condition. If it is not satisfied, then if it's satisfied, we use SKT as our step. If it's not satisfied, we build a model and then we move to the minimum of that model. And we do this for each parameter group separately. All right. So for each parameter group, we build a model. We take another step, another direction, another step length, and then we collect them and move as a sum of those steps. Not sum, but as a collection of those steps. And so this gives an adaptivity of the steps that we are taking with respect to the models. Okay, but how do we build our models at around these 2 points, the starting point and the trial point? So basically what we do is we build two linear models first. The linear model at xk and the linear model here at the trial point xkt. Right? And then what we want is we don't want our point, our minimizer for the model, to be close to xkt or xk, because we know that both points won't work. So what we do is we weight them and sum them with these weights so that this minimum xk plus 1 that we are going to choose doesn't get close to these 2 points that we built the model around. So we choose these two weights. These are the projection of s minus skt and s over the vector negative skt and skt. So you can check that this really prevents this point converging to either xk or xkt by increasing the weight of that, and the minimizer is trying to minimize this whole model, and then if one of these is increasing, then it's trying harder to minimize that. Anyway, so when I say minimizer, actually we are not applying any optimization method to that, because actually we can find the minimum of this model analytically. So this is our model. One thing more is we don't want the minimum of that, the minimum step. We want this step sk that we are going to take to be smaller than skt. We don't want to move far away from these points. So what we do is we introduce this constraint to our problem so that s is smaller than skt, also s minus skt. All right, so it stays somewhere here. It doesn't go up there and here geometrically. So now our minimization problem is minimize this quadratic function with this constraint, It's a constraint minimization problem, and actually we can solve this analytically and find what SK should be, and then once we get it, we move to that point. So here's our algorithm in a nutshell, and we can explain it better like this. So at every step we calculate the stochastic function value and stochastic gradients, take a SGD step, take that as a trial point, check if the stochastic Armijo condition is satisfied. If yes, stay at that point. If not, build a model, find its minimum, and move to that point. So this is what we are doing here. And if you compare this with SLS and other methods with SGD and ADAM, as you can see in MNIST data, SMB with learning rate 0.5 works pretty well in terms of training loss. And also if you look at the test accuracy, it converges to a better accuracy from the beginning even. And this is in terms of runtime. So even in runtimes, even though we are calculating more function values and gradients when we take the model step, still in terms of runtimes it works pretty well. In Spartan the picture changes and SLS performs better, as you can see. But SMB seems to be working better than SGD and ADAM in terms of runtime and epochs. And if you also look at in terms of test accuracy, it's again below SLS, but it converges to a good accuracy before SGD and ADAM do. Now CIFAR 100 and ResNet problem. Now here, this is again interesting that here in terms of loss function, SMB converges very fast to a minimum. But even in runtime and in epochs, but if you look at test accuracy, it falls really behind. So it's again this interesting phenomena, and it's not easy to understand which algorithm works well in terms of generalizations, and it's problem dependent. And one thing to say is, again, SLS has this, auto scheduling. Not that it, find the right step size at every point. It also, lowers the maximum step size that it starts from at every step by looking at the step size chosen in the previous step. So it's kind of an auto-scheduling mechanism to decrease the step size on the way while on the run. So what we did is we tried a very simple auto-scheduling method algorithm. It's a preliminary try. Sorry. Okay, so I forgot. There's this again without any auto-scheduling, SMB versus SLS on CIFAR 100, but another popular, architecture called DenseNet. And on this classification problem, test function is better, minimizes the test function better than SLS. SMB is doing that. But if you look at gain in terms of loss test accuracy, it converges to a good accuracy before SLS does, but stays a little bit lower this time. But if we try some, simple auto-scheduling, what we see now here is SLS is performing better than, SMB model building method with some auto-scheduling performs better than SLS. And here the auto-scheduling is very simple. You look at the model steps taken in an epoch and the ratio of how many model steps you take with respect to how many total steps you took in that epoch. And then here I think if the model step is more than 5% of the total steps you take, you decrease this step size by 10%. And then if it is less than 5%, then you increase the step size by 10%, but there's this maximum step size. Do you provide the algorithm from the beginning so that it doesn't go wild? And then once you do that, even with small, simple auto scheduling, you see improvements on the performance in terms of training function. Okay, what about test accuracy? This time we see an improvement there also. SMB convergence to a better accuracy than the other methods, SMB with auto scheduling, in terms of epochs and runtime. And okay, this is all I'm going to say for this class. Thank you for coming. And see you in the next class.